Hello everyone. We'll continue our geotechnical design according to Eurocode. And in chapter number 8, we are going to talk about hydraulic failure today. It is a worked example, worked example on hydraulic failure. So before starting, I would like to remind you this, what we talked about in the previous lesson. Verification of resistance to uplift. So this is failure due to the water pressure, upward movement of water, and to verify that this is okay, the resistance to uplift is okay, you have to check this equation or inequation, okay? So according to Eurocode, verification for uplift, it should be carried out by checking that the design value of the stabilizing forces, the stabilizing vertical and variable, forces, actions are less than the stabilizing one, So stabilizing forces should be greater, the sum of them should be greater than the destabilizing one, which is written here. So V DST means destabilizing, and we are talking about design one, not characteristic value. We are talking about a design value of the forces or actions if you want. So the design value of these vertical ones, vertical destabilizing forces should be less than the design value of permanent, this is permanent stabilizing action, plus some additional resistance, this additional resistance which may come from, you will see, tension piles or anything that could help to resist to the uplift, So the vertical destabilizing forces can be like this: permanent destabilizing forces plus variable destabilizing forces. This means the V destabilizing. So normally you could just take this, and put it here, replace it by this, replace it with, replace this V destabilizing by all these two, So anyway, we took a few examples last time on dams, and this was what we illustrated here. So the water pressure is sometimes so high that it could lift completely the structure. So this example we are going to do is based on like excavation. So, but it will be still same. We will have to respect this inequation. The stabilizing forces should be less than the stabilizing. If that is not verified, so the uplift failure is not secure, it is not safe. So we are going to do this worked example illustrated by this figure. It is excavation. So we have sheet piles around here, and we have a concrete slab like here. So what we are going to check, and you can see here the water level is like at the ground level. We are going to check if this concrete slab is safe from uplift. If the water coming upward, like in here, will not lift this slab. Yeah, that is what we are going to check out. So the figure is showing ground condition and the cross section of the excavation. The ground condition are here. We have characteristic value of the shear friction angle, unit weight, and the concrete weight and steel weight. The sheet pile are steel sheet pile. And the cross-section information also, we have the thickness of the slab, the height of the or depth of the slab level, and the height, the length of the sheet pile, okay? And also the geometry of this excavation. So as you can see, it's like it's not it's not a channel, okay? You can see A and B here. Oh, these are the dimensions. So it like a rectangular shape. The base of the excavation is has rectangular shape. So first the sheet pile were placed, then the ground was excavated below the groundwater level because the groundwater is at the surface. Struts are installed, then the underwater concrete slab is placed. This slab, concrete slab, okay? Then the water is pumped out of the excavation. So for this kind of situation, excavation must have sufficient safety against failure due to uplift. And this is a transient design situation. From the beginning of this program, I think we talked about transient design situation. So during the construction, reduced safety factor may be used, especially in Germany. Okay. So the partial factor that we can use here, we have partial factor. This is like the names or the symbols. The names are here. Yeah. So partial factor recommended by Eurocode, and these are used in some countries. Yeah, in the national index of some countries. Yeah. But you can see that they are same 110909. Okay. Maybe some country don't use this value recommended by Eurocode. As you can see, for example, here it is different. This one is different totally. It's one Eurocode recommended 1.4. They're using 2. Okay. So that are the small differences of Eurocode in across the countries. But this one, model factor on the wall resistance, okay? Germany is proposing this one, which is very important, okay? Because if the weight of the concrete itself is not enough to stand against the uplift forces, means these vertical forces, the stabilizing forces, then we need the friction, the wall friction, to include the wall friction to check if this enough. You will see step by step how we will do it. So let's put this back here. So as I was saying, first you have to verify only the weight of the structure. Don't include anything yet. Okay, the wall friction, no, you don't have to include it yet. The weight of structure, it means the weight of the slab and sheet pile, okay, to see if they are the stabilizing forces, which in this case are the seepage, the upward water pressure is less than that. If the water pressure is higher than that, then you have to include, then check like a wall friction, and even sometime consider putting, including some resistance like tension piles. So we will see all this in this example. But of course, we will not be able to finish it in just one video, just one lesson, okay? We'll have to come back again. So first, the self-weight of the base slab, okay? Self-weight, it is concrete. So the thickness is 1 meter and the dimension of the section of the excavation is here. So this area, if you calculate this by this, multiply, you will have the area of the section, right? Yeah. So the base slab, it will be the thickness 1 meter like this here. Concrete, it concrete slab, so the unit weight will be like this. Yeah. And then the base area area A, small a multiplied by small b, this by this, you will have the base area. Yeah. So the area multiplied by the thickness, you will get the volume, right? And then you multiply by the unit weight of concrete to get the weight, and that is permanent, right? Okay. So that is a permanent law. So the 50 we are getting here multiplied by this one, it will give us, multiply by this, we get the volume, multiply by the unit weight, and we get the total weight in kilonewton here. Okay. So the total force action, the contribution of the slab, the weight of the slab is 1200 kilonewtons. Okay. So that is uh, permanent action. So, and don't forget that this is just like a characteristic value. You have to multiply it by a partial factor later. So let's keep this and continue with the sheet pile. So I will keep this here. Okay. So self weight of the sheet pile wall now. The sheet pile wall. Don't forget that this is not a channel. So it has 4 sides. Okay. And we have 2 sides of 10 meters and 2 other sides of like 5 meter length. Okay. So it means we have 4 sides of sheet piles. Okay. So the thickness of sheet pile is this 0.03 meter. The unit weight, it is steel. So we have this information here. Okay. So the unit weight of steel is this. Yeah. 78 kilonewton per cubic meter. So the weight per unit area, okay, by unit area, we have to multiply this by the thickness, okay, multiply by one square meter. That's the weight by unit area, okay. Then we can calculate the total area of the sheet piles, okay, and we can then multiply by the area by this unit area, the weight by unit area to get the total weight. So the length of the sheet pipe is this 15 meter, okay, all this. And the area, the section, we multiply this twice because as I said, we have 4 sides, 2 sides of face-to-face sides, 10 meter, and 2 sides face-to-face, 5 meter, okay? So that's why we have to multiply by 2 here. Okay, this will get us the total surface, the total area. And if we multiply this by this value, 2.34, we will get the weight of the sheet pile, okay? Then we can sum up this plus the weight of the slab, concrete slab, okay? To get the total weight of the structure, okay? So don't forget characteristic value weight yet, yeah? So this plus this, 1200 plus 1053, we end up with this 2253 kilonewton. Yeah. So this is what we have. That is the permanent load, permanent, let's say, self weight of the structure. Okay. Now let's go. This, don't forget this. This is the stabilizing force. this here, the stabilizing action. It is this. But of course, this is characteristic value yet. We didn't calculate the design value yet. Okay, so water pressure now. It means we are going now for the destabilizing force, destabilizing action. What is the value of the, you can see the water level is at the ground level, right? And we want the pressure of this here, under the slab, right under the slab, and which is then this H, 10 meter. It should not be here, okay? It should not be here because the slab is here and we want to know the pressure under here. So just don't forget that the section, the area of the base area is 10 by 5. A multiplied by B, which is here. So you multiply it, H by unit weight of water. H is this steps, okay? Then we get this 5,000 kilonewton. So you can already see the difference. This is the permanent resisting force, and this is the destabilizing force. You can see already that it is not safe, okay? So if we suppose that there is no additional resistance, the additional resistance is 0, okay, 0, then here is what we have. Now we are going for the design value. We have the characteristic value. We are going for design value. For this one, the partial factor for this one. So unit the pressure, water pressure multiplied by this, the stabilizing. Okay. And this one as well, same. We have to multiply by 0.9. Okay. So where did we get this? I will go back again in the previous slides to show you where did we get this? It is here, yeah. This, okay. Permanent non-favorable action, 1, okay. Partial factor is 1. Permanent and favorable action, 0.9, okay. So we are not talking about variable yet, yeah. So it's clear from where we got this partial factor. So let's go back where we left. It was here. So multiply by 1, 0.9. The permanent favorable is this one. We multiply it by 0.9. The permanent and non-favorable is this one. So multiply it by 1. So you can see clearly that this is not enough at all. The requirement is not fulfilled. Okay. It is not enough. So it means the stabilizing force is higher than the stabilizing one. Not enough. So what should we do? Next, we have to include the wall friction resistance. Wall friction. What does it mean? We have this retaining, retaining wall, the sheet pile. If you want to remove this sheet pile, there is a resistance, right? Like the friction between the wall and the ground. That will also help a little bit. Okay, it will help. That's why we can consider it to check if by adding that you could make it safe. You could verify that you will add that to the favorable action, resisting forces. Yeah. So how do we do that? Let's go and see. So next, uplift verification, including wall friction resistance R. We perform that and see. So for that, you remember this model factor proposed by Germany. We have to use it to estimate the friction resistance. Okay, so the characteristic value of wall friction are K. So we will treat it as stabilizing action, and we will use the vertical component of earth pressure, active earth pressure, which is reduced by this model factor. Okay, so when we did the chapter on retaining wall, okay, embedded wall and gravity wall, both we did talk about the active earth pressure and how to estimate it using the coefficient of earth pressure for this. So we will need this here. So okay, so that resistance RK, okay, friction wall friction resistance characteristic value from the earth pressure multiplied by tangent of delta A, and uh, these parameters. Okay, so if we get the value of this angle, if you remember, we can get it from the friction angle of the soil. Okay, and also for the earth pressure, we need the coefficient. We need a coefficient. Okay, earth pressure coefficient in case of horizontal surface. Okay, so delta A, small delta, can be obtained from this. Okay, the friction angle, characteristic value of friction angle, which is 32.5 degrees. If you remember, when we did chapter on the retaining wall, this is what we said. And the earth pressure coefficient, KH, which will be used to obtain the earth pressure here in case of horizontal surface and vertical wall. What does it mean? The wall here is not inclined, right? And the surface is horizontal here. Okay, surface is horizontal. So the value of this can be obtained using a table we use in the chapter of retaining wall. Maybe you don't remember, but if you have time, go and check, and we will see it here also. Okay, and we assume that the earth pressure is acting only from outside. Okay, from outside here, not inside. So from this design chart, we can obtain the coefficient of earth pressure. Okay, it will help us to obtain this one. Okay, this angle is simple. This, if we want the value of this one divided by this, you can see here the ratio, this ratio delta divided by 5. Okay, delta divided by 5 is 0.66, 0.1, sorry. Okay, according to the value, you can obtain the value of the horizontal component, like earth pressure coefficient, earth pressure coefficient. Okay, so this is just illustration. Horizontal axis is for the friction angle, which is 32.5, if I remember. So 32.5 will be around here. This is 30, this is 35, 32.5 will be here. And this ratio, since this ratio will be exactly 0.66. Okay, if you divide 2 by 3, you will get about this. So 32.5, this curve, this line, and you project here, you will get around maybe 0.25. Yeah. So this is how you obtain the coefficient of earth pressure. This is just an illustration. Okay? Please check this figure in Eurocode and you will see things about shape. And the tangent, because we need this also, tangent of delta is this one, 0.397. Yeah. So the earth pressure is assumed to act only outer, and this is, we said this before, out, it acting only out. So in summary, we have this, we have tangent of delta A, this one. We have the earth pressure coefficient. So then we can calculate this one, the earth pressure. I mean the earth pressure, then we reduce it by using this coefficient. Okay, so for the earth pressure, uh, 2 multiply A by B, A plus B, small a plus small b, okay, multiply by 2. This will be the perimeter of the inside, okay? Because remember, we have 4 sides. If you do 2 plus 2 multiplied by this a plus b, it will be like you are calculating the perimeter of the base, yeah, around the all the perimeter around the sheet pile, okay, where the soil is, the pressure is acting, that pressure is acting on that, okay. That's why we need it. And then for earth pressure, remember that this kind of thing from up, but at the stop it's 0, then you go deeper, it increases. So if you multiply this by to have this, the value of this is depth L 15 multiplied by the unit weight of the soil, okay, multiplied by the unit weight, which is here, multiplied by the unit weight. Then if you want this total force, okay, you have to multiply it by L again, then divide it by 2 to obtain this area. I think everyone can understand this, okay. This, it is like you are taking this value, multiply by L, okay, then you divide by 2, okay, because if you take this value, this length, multiply by this, it will be the area of rectangle you will getting, okay. You will get the area of this rectangle, this kind of, follow my pointer, this rectangle. So you have to divide by 2 to obtain the area of this triangle, okay. So that's why we have 0.5 here. 0.5 is just 1 divided by 2. It is just the division by 2 that giving us 0.5, okay. And to have this, the value of this one, it is gamma multiplied by L, this total L, gamma multiplied by L, right? Yeah, gamma multiplied by L will give you the value of the pressure here at the bottom. So gamma multiplied by L, then multiply by L again to calculate the area, then divided by 2 to obtain this rectangle. Yeah, I think it is clear. Then you have to multiply by the coefficient of earth pressure, the K we calculated here, okay? And by doing that, then it is done. You obtain the friction Okay, you see that we have multiplied by the total area. Okay, multiply by the total area, the total perimeter. This is plus, right? Plus. So this, like, you are using this force and you turn around the excavation. Yeah. So you will get this in kilonewton. So now you have the contribution of the friction. Okay. Then to obtain that, the R, because so far we have only this. Okay. This. So we have to calculate to add this part. So multiplying by the tangent is here 0.397, and multiply by 0.8, which is the value of this n. Okay. So everything mixed together, if the calculation is not wrong, you will get this 2,680. That the contribution of the friction, the wall friction. Okay. So you have to sum this up with the result we had for the self weight, the slab plus the weight of the sheet pile, right? So, and we verify again. Okay. Remember that for the water pressure, it was 5,000. Okay. Didn't change. The stabilizing force. Okay. And the value we obtained for the total weight, the self-weight contribution of the self-weight of the concrete and sheet pile was this one, 2,253. Okay. I don't want to go back in the previous slide, but it was this value. Plus the value we obtained now for the friction of the wall. Then this is a permanent and favorable force action. So we multiply it by the by 0.9 with partial factor. For this one, the partial factor is 1, so it doesn't change. Permanent and non-favorable, it is 1. So we can see clearly that it is 4,400. It is still not safe. Still not good enough. The uplift is not still verified. Okay. So the uplift requirement is not satisfied. So we have to add some tension pile. Okay. We have to add some tension pile. And that will be for next time. Okay. For today, we will stop here. But I hope you did understand what is going on. So thank you very much for your time, and see you